Hello.
Okay, we are live. I would like to welcome everybody who's watching to the Azure Zurich User Group meetup. This time it's about building a massively scalable C++ compiler using the Azure Cloud. And we quickly share a couple of words about the user group. So as usual, it's me and Thomas. We are the organizers. If you have any questions, feel free to get in touch. Looking at the events that are currently planned, we have finished the Azure Kubernetes Service series with 6 episodes that are all available on SpeakerDeck. You can check out the slide decks and the recordings as well. We have another event planned before the summer break, which is next week on Tuesday. It's the first in-person event this year, and it's going to be the Azure Zurich User Group Container Night at DigiComp in Zurich, very close to the main station of Zurich. We will have 2 sessions, one about Azure Container Apps and another one about how to secure and scan your containers for vulnerabilities using Azure DevOps. The meetup is published today, so if you go to azurezurichusergroup.com, you can register for next week. Please only register if you really want to make it, because we will organize food and drinks, and if we have too many people not showing up, that's going to be a tough night for us. And then there is the partner event .NET Day Switzerland in the end of August, where tickets are available today. And I think that's it. I would like to welcome Damien to the show and hand over to him and wish everybody a nice session.
Thank you very much. Nice to be there. Thank you for having me. I'm really glad I could join the meetup here. It's really mean the picture you selected for the cover of the meetup, like a really old Windows 3.1 MSVC or something like this, or Visual Studio. I think it's still a bit more modern today, and I would like to show what we do at TP definitely. But I like it. I found it really funny for a cover. Okay, so I'm Damien, and I'm actually a co-founder at TP Technologies in Zurich. We with Yannick, we have founded the company last year. Our goal was to make software development way more comfortable, more efficient. Our goal is to have fast build on the simplified dependency management. And for this, we needed to simplify and improve the build process. We have been the last 10 years busy writing build scripts, integrating libraries, making a build system interoperable since for different products in the IoT or in the automotive space or on mobile. And we decided that it was not possible to continue to do that. And that's why with TP we are addressing some of the issue with C and C++. And I would like to show how we built one of the core components of TP, that is our cloud, and how we built the software architecture based on Azure and other technologies that we use, and showing you how we do that. I'm really open also to question and welcome feedback there. So the three main problems with C and C++, usually when I can ask people what it is, they have a lot of ideas. It happens that there are more than three problems, but we at TP, we decided to focus on some of them. And one of the focus was like, how do you make to reuse code in native environment? There is a lot of differences to languages like JavaScript or C# that have like a common runtime that is run the same on each platform, and you compile only once. In the native languages, what you have to compile for the different target platform, you end up having a mess of many libraries with many different compile targets, and it's really hard to actually use the libraries that were built in your code, because they either use an older build system or another build system, or it will need extra packaging on the script building, on script writing to make it usable. So we said we need to solve that to make any code that was written once in native code, C, C++, or other languages in the space like Rust, Go, and other, to make it reusable. And for this, we use code scanning techniques instead of build script configuration. And so we use the code scan algorithm that we built to generate build scripts so that you don't need to write them anymore. And this works for then any platform and in a pretty easy combination. And the other thing is, when you have all the code for your code base and you have all the dependency and all looks pretty elegant and shiny, as our code naturally is, because we only do elegant code naturally, there is still something missing, is like the tools that you need to make them run. Like if you are, for example, the need of some Azure command line tool to set up something, or some Terraform to set up some environment, or if you need to build the compiler to build, or if you need whatever as tools or stuff, it is always like another kind of dependencies that your application relies on. And usually when you have developer onboarding in a project, the developer needs more than weeks to actually get started, because he needs to install all these things. If he has multiple targets to address, then he also needs to handle the installation for all these targets. With TP, we provide environments that are stored in the Azure cloud as images that are reusable for anyone in minutes. So we simply get from weeks to minutes in developer onboarding. And I will come to detail how we make that. And finally, the last thing, and it's the reason why we are building in the cloud, but it's not the only way that we speed up the build process, is compile time in C and C++, or usually on native languages, also like new languages like Rust. It is pretty long, and you can then definitely play some games while waiting on the compiler to finish. And at TP, we have a unique system to build faster at a higher granularity, thanks to a build splitter algorithm. And for that, for the build that we split in smaller parts, we generate way more work. So we need the cloud to execute everything in parallel and bring back the result. And this is something that we are doing. But first, perhaps like, what is perhaps uncommon to it is perhaps uncommon to development in web application and so on, is why would you make C++ for web apps? Because at TP, we build a cloud application which relies on different cloud vendors and on Azure. We joined Microsoft for Startups in the end of last year, and we are happy to be able to use some of the nice features that are in Azure, where we show how we use the Azure DNS that Yannick implemented support for. And actually, why would you do your web apps in C++ and not do it in, I don't know, PHP or JavaScript, or whatever is more likely to be used in this field? Actually, many people might think it's kind of masochism, because C++ is like a cool language, but it's really hard to get running on compiling and so on. But that we solve with TP, so we don't have this problem anymore. So it's not the reason why we do C++ for web apps. It's not because we are masochist or we are crazy. It's really because it has great value when you have a web application at a big scale. And we are like using a lot of CPU resources and managing them. And so the reason why is simply, nowadays, if you take the top 10 million websites and you look at them, you have like, most of them are written in PHP. And all this requires a lot of computation. And if you take away all the internet requests that are for video stream and stuff like this, actually all the user using the request, the web services, just to get content, to fetch content to some dynamic website, it generates more than 1.32 billion CO2 tons on the through the internet, actually. And with C and C++, you could save 47,000 CO2 tons a year if all of these websites would be written in C++. Because if you take the same application running on a typical hardware that you can find in many cloud vendors, and you take a workload that is like 43,000 web requests a second, then one server with a C++ web server, like the one we use, for example, can handle all these requests with just one instance of Dell Xeon Gold, while if you take the same written in PHP or Python, you will need to have 7 servers to deliver this same amount of requests in the same time. And we thought, okay, let's start with something lean. We will add servers, naturally. We are not like scaling horizontally, but vertically, we're more scaling horizontally. But we thought, let's try to make something for the planet and write to application in a way that is not that carbon hungry. And so the other thing is, although you also have like bigger speed in terms of reply to requests, because you can serve more with one server, you also spend less time serving them. So the user have a better experience using your services. And one of the big topic we had when designing the architecture of this application with my co-founder Yannick. He's not in the room, so I can tell a lot of things about him, but I won't, because if he looks at the stream, I'm bad then. We thought a lot about this discussion, microservices versus monoliths, and we aren't done yet. It's still a running discussion, I would say. One thing is, when you architecture a cloud application, if you start with monolith, sure, at some point you will have a problem because you cannot infinitely scale vertically. On all the cloud is about making applications scale horizontally. And the thing is, monoliths have the advantage of being simpler when you have less users. And at some point, when you have more users, you need to scale out. But at the beginning, it's a good way to start with. And microservices are the advantage that, yeah, you can scale horizontally from the beginning. You have an high availability in case of a system that breaks down. And it is, on one hand, it is prone to Conway's law, because typically microservices, they tend to be assigned to some developers. Like one developer makes this service and the other makes the other. So you are just reproducing the communication architecture of your organization inside your software architecture, which might not be actually the software architecture that is fitted to the problem you have. And on the other hand, it requires a lot of marshalling code between the services and so. There are toolings to do that, but I wouldn't say that they are that good yet. I hope it's getting better in the future. And what I found really interesting is from one of the web framework we use is a term that the author of the web framework, Leonid, wrote and he explained on his website, is monolithization. Actually, it's the best of both worlds, meaning being able to decide when you go to microservices architecture on when you stay a monolith based actually on the load of your application. And we try to follow this. Basically, the idea is, instead of writing the microservices as separate applications that lives in a separate memory space and so on, you write all the microservices in library code that you can either load inside one monolith, or when you need to scale, extract as separate executables that are run either inside a Docker container, also on the cloud, or just on another machine. And this is something that I found pretty elegant and that I would like to see more in many languages, and that is actually makes it possible to start a small on-premise deployment just with one app, and also scale it to the cloud on many cores with some executable. As soon as you use the API used to communicate between the different part of the library, and you don't have this overhead of container, because let's be honest, using Docker for microservices or containers in this format is like an heavyweight process wrapper, and it feels like bad for all the energy spent and all this space is used for every app as a Linux within. And so I think it's something that is pretty interesting. And you can get grid isolation still at this level. And what is interesting is that you can see when you run an app with many requests per second, actually, you actually get for long a better performance with monoliths. These details can be found on the same article I shared before. So it is a long time until you need the microservices to scale out. That's why I think starting not necessarily with microservices from the start and being able to switch easily is the future. But as I said, not every language can that, and not every library can that, but it's something I find really elegant. And at the end, so long you don't need that much users, you need less overhead, and it's a bit simpler to manage. And as soon as you can extend, then it gets interesting, and you're still not that costly in terms of overhead. But long speaking about this design topic, we fought a lot with Yannick, and I think I'm the monolith proponent, while Yannick is the microservice proponent. Which is good is that we listen to both, so we found the way in the middle, the right compromise, I would say. And it also helps microservices to integrate different kind of technologies. On TP, actually, it's a tool that scans code, that generates build scripts, and makes build faster thanks to splitting algorithm that splits the workload in small chunks, and that builds these chunks on the cloud. And so to build TP, we set up a first architecture for cloud that is based on a Docker Swarm, but it's mainly containers that we could deploy on any container infrastructure. We are looking very interested in the container day as well to learn about how we could migrate that possibly in this architecture. We have like one main reverse proxy in front of our cloud that proxies the different requests to the different microservices, one dedicated to the front end that can be scaled, one dedicated to handling build requests and dealing with build, and another for file synchronization from build folders to source code. And finally, we have some databases behind that we actually manage in a way that might feel unnatural, but we found really efficient, is using actually JSON-B inside or JSON inside a relational database. It happens that Postgres has a special data type that is binary for this, and the performance and the flexibility that it brings is really interesting. Because you can also forward directly from the database to the end user the information without having to go through an ORM layer if you just need to read them. And I will come to these details a bit later. And then we have what is really interesting in today is we have on one hand the Azure DNS services, and we have cloud data centers. We have different cloud vendors because we have some requirement, but I don't think at the moment we can do everything with Azure, for example, cloud nodes, or simply to have like a backup in case we will break something in some place, being able to still serve our users. But basically what we do is when a user comes and starts his web browser TP build, on TP build, we actually create his account with his private vault that provides him end-to-end encryption for his builds and for his source files. And then on the local machine of the user, where he builds software, or where he edits the software, we actually get the secure vault, and we provide the machine information. We provide the build folder to the storage TP build, and we ask for the TP build microservices to provision us build runners in the cloud, in the nearest data center to the user, so that you have little latency communicating with the remote machine. And finally, we make the build happen. And I can show you how this looks like for superficially in terms of user experience. Let me start a new browser. So whenever a user goes on TP build, when he signs in the first time, he can sign in with GitHub. There we just take his email address and the nickname, and then he's sent the first time he logs in to an onboarding wizard. And in this onboarding wizard, he's asked to create a private vault to secure end-to-end his communications. Whenever he creates the vault, he can link the private repository he has with GitHub. On GitHub with TP, so that the TP build runners can access them. And then he can simply add TP to his machine or to the VS Code that he's running. And then he's asked for TP Connect. And the TP Connect, it's like a way to make your local PC. Here I have a small MacBook Pro with 8 core and 16 gigabytes of RAM. Actually, whenever I do TP Connect, I get the power of the cloud bound to my machine. That means it suddenly extends my machine with the RAM and CPU count from the build runner we start in the cloud. And it's like when I run a command, a build command, or execute unit test or things like this, I actually can run them on the cloud without noticing. That means I not only have a Mac, I also have a remote Windows, I also have a remote Linux, or I can have another remote Mac, but from the size I want. And this is really important for native build workflow. C and C++ build, Rust build, big code base in TypeScript or in Java might require long build times. And with our algorithm plus the TP build cloud, we can speed that up. And we can save to some teams, we have saved 2 hours per developer per day. It naturally depends always on the code base. And I'm happy for you to try to register as well, to try it. If I will do the TP Connect, I will just make it a bit bigger. If I do TP Connect, I just clean the connection because I was already connected. What happens is that I actually get asked to pair my machine with the cloud so that I can extend it with the power of the cloud. So I'm asked with a pairing information that, okay, my PC named Damien Etreg, sorry, it's my nickname since I'm a teenager, did some open source stuff that you can find behind this nickname, the pairing code is the same, and I can grant access to this machine. Whenever I do that, the TP build cloud delivers to the local machine the secure vault, but I have a passphrase that I'm the only one to know, because when you create the vault, it's made browser only, and then it's sent encrypted to the server. And this browser only encryption is done in WebAssembly. And the same module, which is written in C++, is used also locally in the local client. And now I can build actually with the cloud. I will show you soon what it means and what it means to build with TP. But basically, what we did is we registered here, created the vault that was stored encrypted in the database. When I did the TP Connect, I got back this vault provided from the build API and authentified my accounts with the account microservice. And now I also am able to generate keys that give me access to the remote build instance that I can ask for. So TP, it means it's native C and C++, the code base. So naturally, the first thing is C and C++ developer reinvent always all the wheels. You saw it in the meetup invitation, the cover page. It looks like it has been taken, the screenshot has been taken in the, I don't know, 70s or something like this. And actually, we provide a way to avoid reinventing all the wheels, because this is the issue with C and C++ developer. They needed to reinvent all the wheels because it was harder to reuse some library that was made for another build system, made for another completely other platform, or that was like hard to install because there was no solution to reuse libraries. We provide a way to reuse code way simpler. So we decided not to reinvent all the wheels, even if we were tempted. I mean, I see sometimes during the night commit from Yannick doing really hard cryptographic stuff. I always say, hey, why can't we use just the OpenSSL crypto thing? It's safer like this. No, just kidding. But we help reusing code, and for this in TP, it's possible to just like add the dependency you need by specifying the GitHub repository name, and reuse like a library that was out there. So one of the parts of the technology stack we have is this OAuth++ web framework. And if there is a starter project that is available on the TP build that merely contains a base application that I will show briefly. And once we use that, this is the library, and this is like the nice picture. I said like the code is so elegant, but below all this code there is a lot more stuff. And for instance, we use WebAssembly, as I explained. We have some stuff we don't do in C++. I mean, yes, we use WebAssembly in the browser for the Vault, but we are not crazy like doing the HTML rendering on the interaction notification or so in C++. So we do JavaScript with Next in the web front end. We also have for some connector to some APIs, instead of rewriting and reinventing all the wheels, we have some JavaScript code there as well for the account notification. And we use a lot Docker containers for the different services. And we use the Azure DNS to provide an address that is identifiable by easily as something that comes from TP for the build runners. So we register DNS names on request, which is really cool because, I mean, there aren't that much of services like this out there. The one of Azure are pretty easy to use, and to get to bring like under a name a DNS automatically allocated and that we can keep track of. It's really a good thing, I think. It's not something we might think the cloud was thought to use, but was made for it. But I think it's a good tool that we use inside our architecture. And the other thing is the TP build environments that are like Packer image, Packer definitions that represents either Dockers or VMs that represent the build environment where the build happened. Is something that we use and that we build on the cloud. When someone modifies an environment, we launch a Packer build and store the image on the cloud. And we also have Terraform to set up the whole thing. And I don't know if it was like the wiser choice to use Terraform for some of the stuff. We mix it with API calls to the cloud and so on. But it helped us as a startup to get fast on track and to have running a cloud orchestrator that is easy to adapt to different requirements of different machine types and so on, pretty fast and pretty easily. So basically, whenever I do a remote build, and I will show it in the starter, OHTTP starter that I showed before, I actually ask here with the typically to create a machine that is deployed on the cloud and to create a machine or a set of machines that is big enough for my native builds. And so let's get to that. So here we have a small application with this OHTTP starter. What we actually have here is, I will just make it a bit bigger, is like a simple controller that say hello world when with a status code 200 on HTTP when you get it. And to actually build that, in principle, in C++, you should write some build script or configure some solutions in your Visual Studio, which might be a problem if you want to address some other platforms and so on. So you end up with something like CMake, and you should write like CMake that would also install O8PP, that will find it on the system, on the build it, and so on. This is all complicated. With TP, you can just say, hey, I would like to build this project, but for my local Mac. I don't want to use the cloud at the moment. And then you will get the code scanned. So all the files from the project are scanned for application entry point and for dependencies. And for example, here in app.cpp, we have a main function, which is an application entry point in C++. And because the code scanner detects that, it generates an executable based on the name of the file. And it generates also the build script to compile the other files that are dependent there, and it pulls from the specification that we saw before, the O8PP project. I also added the Swagger here, so that we can get like a view on the different API that we have. And here I had some information for the Swagger to bring me the data, and then I could run this this project pretty easily on my local Mac. And so whenever I go to a browser, I can then go on my local application. If I call it directly, I have this hello world. If we look at the raw data, it's a JSON. Okay, even pretty print it on the with the message hello world. And I could go to the Swagger to get the REST definition for it, which naturally is a bit simple because it's just a get. But I could add parameter there. I could add authentication and so on, as we do on the TP cloud. The TP cloud has an API that are full open as well. And so building that was like super simple there. I just had nothing to do. And now if I want to deploy that for a Linux runner or so, I could just say, hey, I want this, but for Linux, so I say TP build Linux. And I also want to build on the cloud with many cores, because 128 cores, it's something that I don't have on this Mac. Whenever I do that, the cloud is contacted. We create a machine on Azure, and we sync the files to actually produce the remote build that is needed. And whenever this machine is created on the remote TP cloud, it actually starts. It keeps the machine up and running for the next steps. Here it's the first start, so there is a cold start happening. So it needs to provision really the machine, set up everything there, and so it takes the first time a little bit of time, and I will show you afterwards that it, on the next runs it is super fast. What is happening right now? It's here machines are provisioned for 128 cores. They are being requested in the nearest cloud data center that is available, and then the files that I add locally, that I built locally, are being synchronized with the remote cloud. That means all these source files, and so I can still continue to edit it locally. They are going to be synchronized in the remote cloud. And we then get them in this intermediary server that is used for the to transfer delta of changes faster. That means when we grow the builder size, and so we can simply provision more VM or rescale the VM and then take back the data from the storage there. We don't use like S3 or thing like this at the moment. We use around storage solution, but we are always improving it, and so it is pretty efficient to then handle any small modification that you do in your local tree to be synchronized back to the cloud. And the thing is, we work with our own product every day, and I think it's really important. And here, as you see, the machine was created. It was the first time, so it took a bit more time to come back. It detected all the dependencies and generated build script for it, built the dependencies on demand, built the starter library, and built the app actually remotely. And so it deploys then the Linux build in the remote session. And I now have the build folder for this, either for Mac or for remote. It comes back here, and I get the binaries that I can run. What is pretty cool is that I can also run stuff there. I can say, hey, then tpt linux and .run, and then I can also run my web application there, like I can do Linux 6617 bin on app, and then run it on the remote machine as well. But what is even better is I can run this build in monitor mode. And whenever I do that, actually my connection stays open to the TP build cloud. I get the TP build environment for me to stay open during the full session. And I can edit the code. And each time I edit the code, I get the feedback that it built or not. And somehow we are seems to be some latency right now. It should have been faster, so I will come to it a bit later. As said, we don't want to end in the situation where our own team cannot use his product, because we think we were suffering under build times, under code reuse topics, and so on. And we had the issue that the build system that we were working on before creating TP were really hard to use. And what we want is to make TP like a breeze to use for software developers, and make them really save time. And so our goal is to never end in the situation of all the developers that are developing it not wanting to use it. So we use it, and we have no build script in our code base. We build on our cloud the releases and so on, which is in turn on the Azure cloud, and through the cloud orchestrator for the Mac instances and for special instances and some others. And we will need even more feedback and even more help from the community, getting to learn what are your use cases. So I would really welcome if you could go on TP build and sign in, try it out, make our platform explode so that we have the scalability issues to fix. And I would really like to know what you think about the monitor mode that you have that I started. So now I am connected to my remote instance, and I can, for example, if I make a mistake in the code somewhere, let's say in the controller here, I make a compiler. I write banana, which is now valid C++. Then the file sync algorithm directly syncs those changes to the cloud. And we see, okay, for this remote build, okay, banana is not working. It's not something valid. So I can delete that and get the build running again. And this happens every time I change something without using any power on my local machine. So I can also start parallelly building on Windows, building on Linux, building on Mac, and so on, and testing if my code works for all targets. Because we build TP with TP, I would like to show how we handle the REST API on the connection to the cloud, on how we build all this stuff. So I already showed this small starter. I don't know if everyone here knows what REST is. I will just shortly say some words about it. REST is not a standard. It's just like an architecture style that provides anarchic scalability, in the sense everyone can fit to the idea of modifying resource in a thread way onto layering URIs as resources, so that you can build way you can build application that anyone can interact with based on the URI schemes. And we use Swagger and OpenAPI to generate our API and to generate a client, so that you don't need to write it manually. And I think it's the right mix in REST to have OpenAPI there, because not having it, it's hard for other to reuse your API. And we have a lot of client and server communication. So here, typical REST request, if you take the most typical example in the REST world and in OpenAPI, is the pet store, where you can have pets inside a web store. And actually, if you want to create a new resource, you call URI from the name of the resource type, and you provide the value in the body, and you do it as a post request. And you want to get it, you do a get on it. So simply, that is REST. And as you saw, we can do with the OSPP service on a framework, we can run on the cloud the REST API pretty simply. You just need to define the endpoint. It is as easy as in other languages. You can specify what you expect for inputs and so on, and you can then generate the OpenAPI spec for it. So you just need to add the info that are needed, additional info, like what is the typical response for 200, and then you can generate the client out of it. And if you want to learn about that, we have at the CPPCon 21 last November or last October, we have made a talk about how we generate the clients with template metaprogramming and in a really elegant way to share code between the server and the client. And now I would like to show a bit of how we interface with the Azure DNS and with the Azure cloud to set up these build machines in the cloud. And actually, we do that in a really simple way. Is that for creating the machines, our cloud generates a Terraform template of the setup that you want. So if someone says I want 128 cores and that many jobs and so on, then we generate a Terraform template out of it. We generate a special namespace for Terraform runner, so that we are not dependent of any others. We do the change and we store all the state information from Terraform in our database. Like we store the TF state and so on, so that whenever we have to do a change back or to modify, we can just do it incrementally on top of it. And finally, when we did this Terraform apply, so we really ask the Terraform software to run and to apply the chunks of the Terraform we run, we actually leave the Terraform operation or the local operation on our own instances. So we create the machine in the cloud. We have the machine that comes back from the Terraform output. That is the main build runner that the end user will speak with. So it's a runner that is made for him. And to this runner, we add Azure DNS entry that allows to be for the machine to be contactable with a clean DNS name. And we manage then in our service the lifetime of these Azure DNS and of these machines. And whenever we need to destroy, we use Terraform to destroy. And naturally, we use a lot of Azure API as well to learn, is it still running? Is it still in the state we started in the past and so on? But it's something that is pretty standard and that we don't need to maintain. It's maintained for us as if Azure will change the way we create machines. With we could simply update the Terraform support in our case, and we will get it. And at the end, we provide some special SSH kind of connection to provide the build command and so on to a reduced set of possible commands that TP supports. And so we then can build remotely and forward builds to these different machines. And what brings us there is we have a lot of actions happening here to create the machines and to create the Packer image that we store in the cloud. But once we did that, the user he gets all the communication that he does. It doesn't go anymore about our own swarm or our own reverse proxy. It goes directly point to point to the machine that is nearest to him, where we can build on where his files are synchronized. So we handle the scalability by design in a way that, yes, if you have many people starting machines at the same time, here it needs to scale. That's definitely something we can. Still things to improve, naturally. Happy to get your feedback on that, on some trials. And then the user gets a direct access. So our cloud isn't really touched anymore by that. It's only the machines that you created for the user that are directly addressed by the TP client. And that's the way we get the fastest response time for the users. And we are not in the way. And we handle pretty easily scalability there. So we can have millions of cores to build in the cloud. We haven't done that yet, right? Multiple thousands, yes, but not millions yet. And it's not something that will impact the cloud directly. It will just be there, and the communication will happen with the users. On this DNS, this Azure DNS, it's pretty cool because instead of forwarding IPs that wouldn't be that private because they are reused and so on, when the different machine changes, and you will have timeouts if it's no more the same, or if the key changed because the IP was readdressed to someone else. We use the Azure DNS service to update all the time the Azure entries. And basically our code that I showed here, that is doing add machine to Azure DNS over the API, is equivalent to doing a command line call of this kind. Like we have the job ID from our database, that has a special resource group associated to him, where all the machine and all stuff lives in there. And then we bring them with specified cloud nodes.tp.build DNS. And so then the user has a direct connection to this entry, and we can migrate the machine without any problem behind. So that's the way we handle the connection there. And we have security that we do in a stateless manner to handle the scale of the different user accessing on the different nodes, requesting this private vault and so on to our TP cloud. So yes, we created the machine in the cloud, they are separated, but they still need to access some data sometimes. And so to avoid having a lock on the database giving us the info about who is authenticated or not, we use JSON Web Token that are signed, and that we provide with, on one end, a refresh token and an access token, where we know actually what is granted to the user. And so during a given timeout, we don't need to access all the time the database. And if you want to use like a JSON Web Token with C++, with TP, you can simply let TP generate it, or write this dependency file to say what you want for base library below the JSON Web Token and which crypto you want to use. And then in the server side, you can simply add with OAuth the decoding and the verification of tokens that you have with the JSON Web Token to authenticate the request. Sorry, and so this is pretty simple and allow totally stateless authentication. And the final thing that we do is kinda, sort of, but not really, an object relational mapping. There is a lot of knowledge in this area. There is a lot of people busy every week with database migration when they do a cloud update and so on. We wanted to do something where we can update our cloud instances independently of the database state and the data model state. So we went for this philosophy that protobuf also follows with optional keywords. And so instead of having something that map SQL tables to classes, we store directly our classes in the database. Sure, we design our classes in a way that they are meant for being stored. It's not like we take anything that is needed at runtime, but the piece of data, the same we use in the application to do algorithm computation, or the same structure we use to provide a dashboard to the user. We just dump it as is in the database. And for example, the machine table that register the DNS name, the IP address, the type of machine, the TF state, and so on. We actually represent it in C++ as such. Like we have the cloud vendor, that is Azure. We have the machine type, that is the different kind of size and stuff that you can have, like standard D8D and so on. Then you have the environment name and hash, that is a TP special thing that where you can create your environment based on in a reproducible way that we archive in the cloud for forever, thanks to naturally Azure images. And we have, like, the last time it was kept alive. And like, what is the execution status? The DNS name here, on the fully qualified domain name, and naturally the other information, like on which subscription does this machine run, meaning on which TP subscription. And finally, the table for that is only data JSONB. And we still have an index on the data ID, for example, because PostgreSQL provides you with that, the possibility to actually address this JSONB data type in a way as if it was columns. And then you have the same, actually it's the same as doing SQL in terms of speed and so, but you don't have the need of an ORM that maps your columns and tables to your classes. When you want to extend your classes, you just add an optional to it, because then the older code that doesn't have it won't, that created data that didn't have it won't crash. And you don't need to do any migration. And finally, when you want to do a query, you just insert this machine structure dumped to JSON inside the database, and you have all you will need following the KISS principle. Keep it simple, stupid, from an ORM, and you have even faster replies, because you get directly the data in the database that you need in the front end or in the client to be transferred. Eventually, you can filter one JSON field away, if really, but you don't have all this construction of data type and adaptation of data types. We have talk at the CPBCon with REST API, actually, that shows how to serialize data in C++ in a simpler way. And basically, our classes can look like this, and it automatically it allows to have a special name for the JSON keys that you want, and then you get your data as it is stored and as it is needed, and you don't need to do any migration anymore because you follow this optional principle. You don't need to update tables. You can rely on index. There is no need to rebuild index. If you would update table, you will need to. And it's faster than MongoDB in terms of performance measured, and it has the same speed as columns. So I only see advantages to that. It makes naturally the ORM people cringe a bit because they like it, and there is a lot of things in there. But I think for many cases you don't need that, and you can get away with data migration that are complex by just handling that in a simpler way. So last word, and then we finished. TP build deploys many cores machine. That's true. And for this, for example, you can specify the environment with a Packer file that either refers to a Docker or that is a virtual machine spec, and with a toolchain file that specifies which kind of C++ flags you will, or C flags you want to use for your build. And when you do that, it creates the machine with a Packer as execution in your cloud, stores the machine in the cloud, in the Azure, and then provides you with the machine ID back, and then we terraform the start of the machine with this image based on the need that you have in size at the moment. The point is, we had some thing because of C++, because it's all, not everything is that pretty in C++. And mainly it happens that you forget to check for a null pointer, and we have like zombies in TP build on our cloud. We had like all our Docker getting crazy. on or Swarm reallocating many more VMs because we had actually in our code a way to dump the stack trace of the program. And it happened that dumping the stack trace was so slow. When someone did a remote build on macOS, we had a bug that ended up trying to find a macOS machine of 128 cores instead of making many smaller ones. And then, because it didn't find any on any cloud vendors, it returned null. And then it dereferenced in the code to null pointer, which was like a bug. But the cloud continued to work, but really slowly, with many instances running at the same time, like in a really crazy ways, because all the code was busy printing out the stack trace, because we had installed the stack trace printer in a way that was using a local tool. That means for every stack frame, it was taking the full binary image of TP and reading it through and generating the address where the crash happened in this stack frame on the name of the function where the stack frame happened. And this make like many call to Azure to line. That was a small binary, but run on a big code base on that scale. It made everything run, and then we had many of the cloud instances still running, but crazy printing stack trace and still replying to requests because the other thread that didn't crash were still running until we get to this std abort. And that's the way we got some zombies in TP build. Now it's fixed. TP is ready for you to use. We'll be really happy to learn more from you and get more feedback to know if TP is the thing that brings the best build times, the best code reuse experience. And we are going to bring other languages soon and provide cross-languages builds soon as well. So definitely looking forward to speak to you. If you're interested, don't hesitate to even call me. My phone is here. Or simply write a mail or register on tp.build. It's just one click away and 1 minute away of having a pretty amazing cloud build environment for C and C++. Thank you very much.
Perfect. Thank you, Damien. Thank you, everybody who was watching. If there should be any questions, feel free to get in touch with Damien directly. And I wish you all a great evening.
Thank you very much.
Bye-bye.
Thanks for the occasion, and see you next week.
See you next week.